power functions. Power functions. When we talk about power functions, we have to know the power. Power. When the exponent is a positive number, for example, n is a positive integer, positive or natural number. This symbol stands for the set of all natural numbers from 1 to 3. Okay. Then, if we have A5, how to define? The exponent which is a negative integer. This one is defined to be 1 over a raised to the nth power. Of course here, a is not 0. For example, a raised to the minus third power is 1 over a to the third of course we can write this as this one. And if these two numbers are the same, for example, a positive 3 and negative 3, then they are all cancelled, equals 1. So we define this number by 1 when a is not 0. A is not 0. So we have this definition, and this definition. So until now, the exponent is an integer are all defined. Sometimes a is arbitrary. Sometimes a have to be non-zero. In these two cases, well, how about this one? This one is defined to be this nth root of a. Nth root of a. So, of course, you never. When n is an odd number, a can be positive, negative, or 0. If n is an even number, then inside this root notation, a is a non-negative number. So, when we talk about power functions, we need to know the meaning of power. This is what? Okay, number system. You could use a ruler and compass, yeah, to explain everything. Suppose there's a straight line here, and we use a unit 1 as a 1, then we have 1 and 2 and 3 and 4. This is exactly whole numbers. 1, 2, 3, 4 are whole numbers. 0 additive identity and expand to -1. Okay, let's consider positive. Then we consider this form. Number of this form is called a unit fraction. Unit fraction. If we suppose divide 1 into 3 equal signs, then we obtain 1/3 or 1/3. One-third. So we have this unit fraction. Once we have unit fraction, we can use 1/3 as a newer unit to define the fractions. So from a whole numbers, to a unit fraction, in the two fractions, therefore, if a number is a fraction can be expressed by a ratio of two integers. For example, this is m, this is n. This one is defined to be nth root, the nth power. But there's something have to notice. Because, for example, 1 can be expressed by 3/3, and also can be expressed by 6/6. And 1/2 can be expressed by 2/4. If a negative integer can be considered, there are many expressions. Equal means they have the same length. For example, from this one here, 3/3, and the 1 have the same length, then we use this notation. Okay, so here we face to some problem. If we write this one, then this is half 1. But if we 2/3 is the same as 5/6, 4/6. Then by that definition will be because here is an even number. When this is an even number, inside the root notation must be non-negative. So, disaster. Here we need to, we require this number in its lowest term. It means that of course, when n is an even number, a is a, we assume a is non-negative. So here, if we require this fraction in its lowest term, okay, I mean already reduce to the simplest as small as they can. And this expression is unique. It's unique. There is only one way to express a fraction in satisfying these two conditions. 我的意思是说哈，分数啊，我们除了整数之后就讲单位分数，再进而讲到分数啊。小学是这样讲。讲到分数的时候，会讲到等值的分数。等值的分数，因为有太多种，我们有一个很重要的观念就是最简分数，对吧？最简，不管分数你怎么写，最简分数的表示法只有一种，可以吗？ No matter how you express and fraction, you can. But its lowest term is only one and one, just unique expression. Okay, so every step must be very careful. Otherwise, you will lead to some contradiction. Okay, so here, just like you have learned in elementary school, from whole numbers to unit fractions, then fractions. But maybe in the 5th grade, the teacher in fact, this equals this. These two numbers are the same. So if okay. I had better write down in this way. Now we have a number line. The teacher maybe told you fractions maybe are not all numbers. Maybe not all numbers. From these observations, we know a number maybe can be expressed by a line segment. Conversely, if we have a line segment here. Okay, if this is a number, real number, R, okay, maybe this position is not a whole number. Then we subdivide this one into 10. Okay, if it happened, this is the 4th this position, then we can express this by 1.4, means 1 plus 1/10. But if this is not, maybe here, more than this one, we may subdivide this small interval into, again, 10 equal signs to have 1/100th, one maybe. Okay. Continue in this way. Eventually obtain a decimal. So decimal. Decimals. Every number, I mean positive number, can be expressed by decimals. Okay, a whole number with 4 tenth. This is 1,000th, 10,000, and so on. 所以我们学了这个整数、单位分数之后，我们发现呢，都可以用长度表示。反过来讲，你的长度是不是一定是分数呢？至少我们都可以用小数表示。我们把那些小数叫做实数、正实数。Then something, we can express some numbers in terms of fractions, but we can express all numbers in terms of decimals. For example, if one decimal is 1.414141, and in this pattern, if we denote this kind of decimals by that notation, then if we multiply R by 100, we will have 141.41. Then we find there's difference. So this kind of decimal or real numbers can be written in terms of a ratio 142.99. Aha, this is a fraction. This is fraction. Okay. This is a fraction. So decimal equals a fraction. And we call such a number, because this is a ratio of 140 to 99, then we say this number is rational. Rational means that it can be written a ratio of two integers. A ratio of two integers. But this, okay, in your history, you know this means a ratio of two integers, right? But in our island, in this island, people, unfortunately, we use a translated object. We call such a number 有理数, meaning reasonable number, not ratio. 应该是两个整数比的数，可比的数，可以乘两个整数的比的数，把它翻译成有理数。照理说 rational 是来自于 ratio 这个词，而不是说合理的意思。有些实数就是小数啊，可以用两个整数的比来写，我们把它这种实数叫做可比数。那我们就说可以写成分数的，就是实数。甚至有人说实数有分数跟不是分数的，是分数的就是有理数，不是分数无理数。这个有理跟无理是很奇怪的，应该是可比数。
The translation is more in the sense of something that is rational instead of the great.
Yes. Well, why a number is rational or irrational? Sounds reasonable. Sounds reasonable. It's quite odd. In fact, this one comes from this kind of decimal. This kind of real number can be expressed in terms of a fraction or a ratio of two integers. A ratio. The key point is this one. Okay? 所以你们知道了哈，我们只读翻译的东西或只做题目，有时候都不知道东西的真正的想法，数学变得很辛苦。Okay. Therefore, let me ask you. Yes. Now we already have powers to numbers of to rational numbers, because every real number, if that real number is a rational, then the number can be expressed by a fraction, and its lowest term is unique. It's unique. So we have its denominator, which is a positive number. Maybe the numerator is a negative number. Is okay. No? That's exam. Suppose with A, this is exponent. This is a number. If m and n are natural numbers, then certainly we have this equality. Even if n is maybe cancel. So when m and n are integers, this relation is still valid. It still is true. Again. Of course, if the exponent is a negative integer, we assume the base is non-zero. Okay. Secondly, if this one is the product of two numbers, for example, yes, 6A, and the grouping, the first group, second group, third group, 3 groups. Each group consists of 2 A's. And even if one of them is negative, it's also true. Well, suppose we have AB here. So here is a to the minus third, a to the minus third. Because this is A and B are numbers, we may consider this. But this usually when we talk about exponents or laws of exponents, we only focus on these 3 formulas. This one is called binomial theorem. Will be considered when in topic of permutations and combinations. So let's stop here. Anyway, when A and B are positive, when A and B are positive, all of them, these three formulas are true. You can verify by some specific numbers. So finally here, when I was in senior high school, yes, not junior. There is a problem like this. -1 can be written as this is true. Then it must be something wrong, maybe. Or otherwise our definition may be inconsistent. Okay, let's examine this one equals this one. This is right. Because 3 is an odd number. This is right. And this is also right because this is exactly the definition of a unit fraction. When this exponent is a unit fraction. And fractions are decimals or a real number. Real numbers. So this one equals this one is right. You should know this. Yes, this example shows every decimal similar to this number, I mean some pattern occur repeatedly, can be written as by a fraction, a ratio of two numbers. Conversely, a fraction always can be written in a decimal of this, how to say, repeating the decimal, right? Repeating. 循环小数. Okay, for example, how to express this as a decimal? Of course, we divide 3 by 7. No. The remainder must be 0 or an integer less than 7. Here is 2. Six less than 7. 4 less than 7. Five less than 7. One again less than 7. But the number is less than 7. The number is less than 7. Only 7 numbers satisfy this relation. Oh, 3. Same means repeating. So this shows that a repeating decimal always can be written in a fraction. Conversely, a fraction, because the denominator is a number. The remainder only has finite many of numbers can occur here. So if 0 is occurred, then already stop. Repeating by all zeros. If no 0 occur, because only finite number can be used, so must be repeated. So repeating decimal, if and only rational. 所以刚才这个地方你们在国中就有学过，凡是循环小数都可以形成分数。反过来讲，分数都可以形成循环小数。那么不能形成循环小数的，那种叫无理数。无理数，因为这充分必要条件。So the real number system or the set of real number can be written as the set of rational numbers and irrational numbers. And these two sets are disjoint. Okay? Every repeating decimals is a fraction. Conversely, every fraction is can be is a repeating decimal. So we call a real number which can be expressed by a ratio or a fraction is called a rational number. Well, what happened here? Can you point out which one may be false? Which step is wrong? This is right, and then this is right by definition. This one are the same. Because one third already the same. So 1/3 equals 2/6, same. And this one, according to this law, yes, this number equals the product of two and 1/6. And this one equals 1. Anyway, from here to here is right. From here to here is right, so I think this is not correct. Because when we use this formula, I mean, if you want to use any formula, apply any formula, you have to check the assumptions. This formula is valid only for the base, if not for all numbers. Sometimes it may be negative or positive. Here, these two are different because this is -1 and this is 1. So when m equals 2 and n equals 1/6, then this is not that. Because the left hand side is -1, the right hand side is 1. Be careful. If you want to apply some theorem, some law, or some formula, please check the conditions first. Okay. After algebraic, arithmetic or algebraic about operations, addition, subtraction, multiplication, and division, and some powers and the roots. Next, we will consider order. It's less than order. The limit related to order. the precise statement, please see the textbook. Here, suppose we have two functions f and g, and when x is near a, since we are talking about limit, so a should be ignored. Should be ignored. Suppose a is a here. A. When x is near a, the meaning of this statement is if we can find some neighborhood about a, maybe the radius is small, maybe. And on this radius, and yes, in this neighborhood or on this neighborhood, f here, g is here. And suppose these two functions, the limit of these two functions as x approaches a exists. These two limits exist. Then the smaller one, whose limit should be smaller? This is f is smaller than g. Then the limit of f at a is smaller than the limit of g at a. Same, when we talk about a limit law or theorem, not only hold for two-sided limit, also hold for one-sided or limit at infinity. Okay. Next, squeeze theorem. Squeeze theorem. P. At this time, we have three functions. One is f, maybe here. Another one is h. This is a. Okay, when x is near a means you can find some open interval or some neighborhood above a with some radius, maybe the radius is very small, maybe. And the three functions g. Suppose these two limits, limits of larger one, the largest one and the smallest one, it exists and the same. Then the middle one, the limit of the middle one exists and equals L. Equals L. This is a squeeze called squeeze theorem. As a name, squeeze theorem. Okay, so almost all limit theorems or limit laws are introduced, have been introduced. So the next, we have to see some examples. Example 4. Maybe I already saw it. Would you please see with the examples I saw last time. Yes, last time. Last time. Okay, good. So, I didn't solve this yet. No, okay. This function is a polynomial function. Polynomial function can be obtained, always can be obtained by finite many steps of addition and the multiplication of constant function and identity functions. So these two operations and constant functions and de-identity function. But we already know for constant function, the limit can be obtained by direct substitution. And also for identity function. Identity function means this one, identity function. Constant function means number. And use the limit laws. This limit can be evaluated by direct substitution. I mean, x squared is x times x. Okay? Limits, if they all exist, preserves addition, subtraction, multiplication, even division. So we only use addition and multiplication. We only use constant function and identity function. After finitely many steps of operation, the operation only these two operations, addition and multiplication. So this limit can be evaluated by direct substitution. X equals 5, 25, 50, 35, 39. Also, rational function can be obtained by addition, subtraction, multiplication and division. Or use these four operations after finitely many steps together with constant functions and the identity function. So if the denominator is non-zero, according to the limit law, we can evaluate this one by direct substitution. Let x be minus 2. 8, minus 8, 8 canceled. And this is 11. Okay, so the Leonard laws help us to find limit. Okay, take a break.